In this video, we're going to deal with linear recursion versus linear regression. Starting with linear recursion, here we have a common difference that we want to take a look at. A common difference is a value added to calculate the next term. So we have one term, we add the common difference in order to get the next term, and then add to get the next term as well. Or it's the difference of consecutive terms. If we have two terms that are right beside each other and we subtract them, we should get the common difference, and that should happen from two consecutive terms to the next two consecutive terms as well. You should get a common difference. When we start writing rules for linear recursion, we have a recursive rule and an explicit function rule, or just a function rule. If we're given a sequence of numbers similar to this, we have the beginning term is 3, and then we increase by a value of 9. It looks like 3 plus 9 is 12. 12 plus 9 is 21. So we have a common difference here of 9. So we need to first identify the common difference in some kind of sequence that we're given, and then we need to identify the first term. So we have the first term is equal to 1 or is equal to 3 in this pattern, in this sequence. Now recursive rule is applied in order to show the pattern. We show the pattern by having one term and its consecutive term and the next term after that and the next term after that. We go from one term to the next. We do not jump around. We cannot calculate a term without having the term before it. So it is a pattern and the demonstration of that pattern. So here we have m sub n plus 1 equals m sub n and then plus d. Now these two here are variables based on where you're at in the sequence. So the recursive rule for this scenario down here is m sub n plus 1 equals m sub n plus 3. This is the recursive rule. And in the recursive rule, all we show is that we take terms and add 3 to it. We don't know what those terms are, so they're left in variable form. Now in the explicit function rule, we can take one term and the common difference, and we can find any term in the sequence. So we have any term in the sequence is equal to the first term, so m sub n is equal to the first term of 3 plus n minus 1 times d, which is 9. And I need to go ahead and change this here. This d is 9 and not 3, and that was my mistake. So we have the explicit function rule 3 plus n minus 1 times 9. And in this explicit function rule, we can simplify this rule and we can combine like terms and have a little bit different rule to show for it. So first we would distribute the 9, and then we would get m sub n equals 3 plus 9n minus 9, and then combining your like terms, your explicit function rule now looks like 9n minus 6. And if you take a look at that and look at it maybe a little bit in depth, negative 6 would be the term that comes before 3 if we were to go backwards in this sequence. If we were to subtract 9 from 3, we would get negative 6. So this here follows the pattern if we were allowed to go backwards. Now if we want to look at linear regression, first thing I want to talk about linear regression is this is when we take a table of data, put it into the calculator, and calculate a equation of a line that best fits that data. So linear regression is essentially finding the best fit line equation or the trend line equation. One of the first things that we're given is a comparison or a correlation to the scatter plot section of this unit. We have the correlation coefficient. This coefficient here determines strength and direction of the data that we're given. So we can tell if the best fit line or the trend line is a good approximation in order to use for predicting future data. So the stronger that this correlation coefficient is, or the closer to 1 this correlation coefficient is, the better the data is in terms of fitting that linear model. And then we have y equals mx plus b, which is the equation in slope-intercept form, which most of the students have seen in all of their math classes in high school up to now. Or we have the second linear regression option, y equals b plus ax. Now if you look at these, then they're not really different with the exception of the a and b. The a and b is something that allows you to have a little continuity between linear regression, quadratic regression, exponential regression, so on and so forth. But the y equals mx plus b is something that has continuity in what they've learned previously. So this here's your previous knowledge. This here is your knowledge in order to use the calculator for further different regression equations. The discussion here needs to be that M and A are the same value. Obviously, it should be obvious that B is the same value, and it should be obvious that these two equations are identical, just they're not written in the exact same form. But M and A both give you the same thing, which gives you the slope, and that is a discussion because most of the kids who are unfamiliar with the technology will see both of these equations and say, which one do I need to use? Do I need to use the first option, mx plus b, or b plus ax? I don't know. And then you go into the dialogue saying these are identical equations. M and A are the same value. It's just written in a different way. And then looking at the correlation coefficient in a little bit more depth, this is the range of the correlation coefficient. It will never be less than -1, and it will never be greater than +1. -1 tells us that the correlation of this data is negative. As x increases, y decreases. +1 is just the opposite. As x increases, y increases. And then the closer they get to 1, that is the closer the dots or the points on the graph get to the trend line. So if we have something that's negative 0.985, we know that the points on the graph are so close to a line that there's almost no space. But because it's not equal to -1, there is a little bit of space. However, if we then get a correlation coefficient that's 0.425, now we know that there's significant amount of space between the points on the graph and the best fit line. And then just a simplistic look at a table for linear regression here. The x and the y variables, those are going to be given to you in real life terms. So this is just kind of an idea of what we're looking at. But whenever you start to identify the y column and the x column and know whether you need to do linear regression or use linear recursion is whenever you look at the difference in x and the difference in y. Here you can see that the difference going from 1 to 4, each term moves by 1, and then 4 to 7 moves by 3, 7 to 12 moves by 5. In order to use linear recursion, we have to have a pattern and we have to have a common difference between these terms. In order to have a common difference between 4 and 7, we have to have the common difference between 3 and 4 divided by 3. That gives us that common difference. If that difference does not equal the same difference for all these others, then we're not going to be able to use linear recursion. We're going to have to put this in the calculator. So here you should be able to see these increase all by 2. So the common difference is 2. Looks like we can use linear recursion. But then here we see a common difference between these two of 6, or we see a difference of 6. But if you take 6 divided by 3, now you get 2. Well, that fits in line with our linear recursion. And we could potentially write a rule using linear recursion based on this data. However, if we see here, this is a difference of 11. 11 divided by 5 is a little bit more than 2. So now we have data that needs to be estimated or approximated with our technology, with the calculator, and then we can get a linear regression equation or a trend line equation for this data. And that is linear recursion and linear regression.